So quality of service fairness, the ultimate goal is to ensure that the systems we're building across the cognitive services are designed to provide a similar quality of service for demographic groups that might otherwise be impacted differently by those systems. So some examples of groups that are typically used across the services in terms of understanding quality of service are ancestry, gender, age, skin tone, regional accents. And some of these are more specific to certain technologies than others. So for example, regional accent is very specific to speech technology, whereas skin tone, for the most part, is specific to vision technology. And so again, the goal here is to think about how the services and technologies are working for these different demographic groups. And I'll give an example starting with face verification. So looking at the image below, a very common face verification scenario is an end user of the face verification API would have some enrollment database where they've stored licenses and license images, for example, of the various users in their database. And then when the API is called, an image or a selfie of that user is compared to the image of the licenses, and a verification is done to sort of confirm if it's the same person or not. And so the goal in this context is to ensure that the face verification technology works equally well, regardless of the skin tone, gender identity, age, ancestry group, and other demographic factors that might impact the quality of service. And by the way, people can jump in during this presentation if there's any questions on what's being presented. I try to sort of save a lot of time for Q&A, so feel free to just unmute and ask questions if needed. Okay, so another example, another commonly used service is speech to text. And so if you look at the graphic on the bottom, speech to text is basically taking in the input speech of a user. There's a combination of both language detection happening as well as transcription. So first, the technology is determining what languages are being spoken by the speaker, and then there's a transcription that turns that speech into text. And so in terms of quality of service fairness, the important thing here is to ensure that the transcription technology and the end-to-end speech to text works equally well across things like regional accents, age groups, socioex, and other demographic factors that might impact quality of service in this specific context. So why does this all matter? At Microsoft, we aim to build technology that empowers everyone. And when you want to empower everyone, you ultimately have to be able to essentially confirm that the technology works well for everyone. And in terms of the tracks at Hack MIT, I think the common question, regardless of what project or which domain you're working in, should be, how do I ensure that my project works well for everyone? And I'll go over a sort of conceptual framework that can help you in terms of thinking about this and thinking about how well a project or system works. And this is a framework that's kind of at the core of my role in terms of quality of service fairness. And it's called disaggregated analysis. So if you look at the chart on the left, imagine that there are 4 different populations for which you're sort of measuring the accuracy of some type of system. If you were to do an aggregated analysis, meaning that you aren't doing an analysis per population, but you're just thinking about the overall accuracy, then you'd make a statement like the overall accuracy of the system is 90%. And on the surface, that might seem acceptable, and there aren't many more conclusions that can be drawn from just that. On the other hand, if you were to think about this in terms of a disaggregated analysis, there are a few different points you could make. One, you could say that the maximum absolute disparity across these population groups is 20%. So if you look at population C versus population D, you see that there's a 20% gap in terms of accuracy. You might potentially conclude that population A and D may need to be further investigated in terms of why there's lower accuracy in those populations versus in B and C. Or on the flip side, you might actually conclude that the training data for the system was skewed towards populations B and C. And so the kind of key point here is that you kind of need to dig a bit deeper than just the aggregated analysis to really be able to understand the performance of the system and to kind of draw any meaningful insights. And so I'll go one level deeper using the same exact data, except now I'll sort of split it another axis. So this is the same data that you were just looking at, but now what I've done is I've split the populations between two age groups, where one is lower than 30 and one is above 30. And so once again, if you think about this in terms of an aggregated analysis, the overall accuracy of the system is 90%, because again, it's still the same data, and we're just considering the overall accuracy. We're not thinking about per population or per age group within a population. Now, if you think about this in terms of a disaggregated analysis, similarly, there are several conclusions that you might draw. Now that we're looking at both population and age group, the conclusions are actually slightly different than before. So for example, now we can actually see that the maximum absolute accuracy disparity is actually 40%. And you'll note that population D, age under 30, is what's kind of causing that big gap. You might also conclude that the group to investigate within population D is specifically the age group under 30. And similarly within population A, the age group under 30 is also something that you'd want to investigate. So the kind of takeaway here is that in terms of thinking about the performance of a system, as you kind of combine different axes, so I'd listed things like skin tone, gender identity, ancestry, and you think about the disaggregated performance of the system, you can really start to kind of understand if the system is performing fairly, and you can actually start to kind of take the next steps of improving the gaps if there are any identified. So in terms of,
sorry, I just wanted to step in here. We had a question from the Slido related to different demographic groups and stuff like that. Someone is asking, Tashu is asking actually, what technical changes are made to the program that wouldn't be made otherwise to acknowledge these different demographic groups?
Yeah, so I have one more slide, so let me just quickly say this and then I'll touch on that. So one of the kind of foundational papers that started kind of diving into this concept is titled Designing Disaggregated Evaluations of AI Systems. So if you search that up, you'll find kind of the paper on this topic. There's also a tool for analyzing fairness of AI systems called FairLearn that you could also look into to sort of more deeply understand or even do some analysis yourself if you're building an AI system. So back to the question of what technical changes, and to make sure I understood the question, was it what technical changes are made to basically improve the system once these performance gaps are identified?
Yeah, once the different demographic groups were added or acknowledged.
Can you elaborate further? Like, what do you mean by acknowledged?
If I'm understanding the question correctly. Oh, go ahead.
I meant like how would the program itself, because already like whenever we implement AI or machine learning, I I think it already tries to modify the program depending on who's using it, right? So in terms of like demographics, what in order to acknowledge for different different people using it depending on their different traits, what exactly like in terms of technical changes would be made to the program?
Got it. So I think the complication here is that in building and designing an AI system, oftentimes these demographic attributes aren't considered, like in terms of the training or the development of the system. And what I was sort of describing is actually testing or evaluating the system to see how well it works across the demographic groups. But in terms of sort of considering the factors, even in terms like building the system or training the system, you could think about like what is the makeup of the training data that's being used to sort of build the model. But yeah, typically the demographic factors are actually considered in terms of building or training the system. I think it more comes into consideration when you're actually trying to test or evaluate the performance of the system.
Okay, and sorry, just a follow-up question. So usually when training the system itself, then is usually like a majority used instead of like instead of accounting for like minorities?
Yeah, so this is another complexity, right? Like if you're building a system, say for face verification, and you like scrape a public face data set, there's sometimes no way to actually confirm that the training data is diverse enough across these different demographic groups. And that's a separate challenge in and of itself. I think right now, where things are in the space, not just at Microsoft, but in terms of thinking around the fairness spaces, after sort of doing the testing and evaluation of the system and identifying different gaps, then you can kind of think about, okay, like, do I need to seek more training data from a certain population group? Do we need to tweak the model in some way? And so a lot of that is kind of after the evaluation as opposed to at building time.
That makes sense. Thank you.
Yep.
Oh, and also if no one else has any questions for Fairlearn, so that analysis tool is used to make sure that people of all demographics are taken into account, right? When training data or like afterwards when we're refining the program.
Yeah, so Fairlearn analysis is specifically for evaluation or testing a system. One of the important things in using an analysis tool like Fairlearn, though, is that the data actually needs to be labeled with the demographic attributes so that you can analyze like the performance of the system across those demographic groups.
So would Fairlearn be used for other purposes instead of only like demographics, maybe also to take account of different people's education levels or whatever factors there might be in other programs for like, yeah.
Yeah, that's a good question. So ultimately, whatever metadata exists can be used in the Fairlearn analysis. So like in the case of face verification, say in the data you have not just like skin tone, but maybe you have like lighting condition or something that's not specifically a demographic attribute, but maybe you want to sort of analyze that with another attribute. So ultimately, if you have the data labels, then you can do the analysis. But I think the key thing that it's offering is that ability to do the disaggregated analysis, like I was showing. But what the user needs to come with is the labeled data to then pass into the system.
Oh, by labeled data, you mean so like the user itself would categorize the different demographics, and then what the program would essentially do is see what percentage of the program accounts for that certain data set.
So not the program isn't figuring out the breakdown of the data. It's more so doing an evaluation across the different groups. So like when I showed population A had an accuracy of X versus population B had an accuracy of Y. What a tool like Fairline is doing is producing that chart with the accuracies or other metrics for each subgroup.
And then how would it?
Go ahead.
Oh, sorry. I was wondering how would it measure accuracy? Because if the program itself isn't trained with enough data to take account of demographics, then how would Fairlearn itself be able to identify accuracy in terms of that?
Yeah, so I think a lot of this would sort of be easier to understand if you actually test the tool, but the user of Fairlearn defines the metric that they're using for evaluating the system. And what the tool does is takes that metric and applies it across the different subgroups. And so the labeled data is being used to sort of break down the analysis into the disaggregated analysis. I can go back to the slide to sort of make it more concrete. So imagine that you were using Fairlearn and the labels that you had were population and age group. And so every single sort of row of your data set includes population, which is one of these 4 options, and age group, which is one of these 2 options. And then you define some sort of accuracy metric that ranges from 0 to 100. Fairlearn would then produce this chart, which is showing the accuracy across these subgroups. And so it's sort of producing the disaggregated analysis, but you're bringing in the data that's labeled with the groups that you want to disaggregate. Is that clear?
That makes sense. Yeah, that definitely does. Thank you so much.
Yeah.
Oh, also, sorry, yeah. I went to the website and it seems like I could see the publication, but if we were to actually test this on applications that we're making ourselves using AI, is there a way to do that?
Yeah, we have a few minutes left, so I'm happy to kind of answer more questions via email if the host could provide my email. But there's definitely ways to do that on applications that you're building. And if you check out the sample notebooks, they should also give you a sense of how to apply that to your own scenario.
Sounds good. Sorry, was your email at the beginning of the presentation? I might have missed it.
Let me send it in the chat. But it's just my first name dot last name at Microsoft.com.
Got it. Thank you.
Yep. Any other questions?
I think we're good on questions for now. So if you would like to continue as much as you can, you can go ahead.
Okay. Well, then I think we can end the meeting. But like I said, feel free to follow up or email me if you're curious about actually using the tool on a project that you're working on.
Sounds good. Thank you so much.
Yep. Thanks, everyone. Good luck.
And a huge thank you to Microsoft. Thank you for coming out.
No problem.